Now coming to the kinetic theory of gases, here we will be doing that is, according to the kinetic theory of gases, we are going to prove the Boyle's law, that is Charles' law, and the Dalton's law of partial pressure. Alright, that is, we are going to explain, or we are going to prove it, this particular three gas laws by the help of kinetic theory of gases. Okay, so now first we'll come to the Boyle's law. Alright, first we'll explain the Boyle's law, or we'll prove the Boyle's law from the kinetic theory of gases. Now let me tell you, Boyle's law, what it says is that pressure is inversely proportional to volume when temperature remains constant for a given mass of a dry gas. Alright, P is inversely proportional to V when T remains constant for a given mass of a dry gas. That is what the Boyle's law suggests us. Now we have seen it from the, that is, we are going to describe the Boyle's law. So the kinetic gas equation is PV is equal to 1 by 3 mnc square, where P is the pressure, V is the volume, m is the mass of one molecule of a gas, n stands for the number of molecules present in the certain volume of gas V, and c is the root mean square velocity. We can say that. Now we can also write this one as 1 by 3 mc square, where m stands for the molar mass, because m into n, mass of 1 mole of the gas into number of moles, will give you the molar mass of the gas, mc square. Now this equation I can write it in this way also, that is 2 by 3 into half mc square. I can write, same it is, 2 cancels, 1 by 3. Now why did I write it? Because half mc square is kinetic energy. So PV is equal to 2 by 3 Ke, so to say. Now next is, from one of the postulates of kinetic theory of gases, we know that Ke is directly proportional to T. From one of the postulates of the kinetic molecular theory of gases, we have studied already. Now Ke is equal to K into, that is T, we can say. Ke is equal to Kt. Now we can put it here. Let us say this is equation number 1 and this is equation number 2. So we can put the value of 2 in 1. We can put the value of 2 in 1 when we put the value. So what we will get? PV is equal to 2 by 3, that is 2 by 3. That is, instead of Ke we can write Kt. Now see here it is. K is a constant, we know, is a proportionality constant, because K is directly proportional to T, where K is a proportionality constant. 2 by 3, of course, it's a number, it's a constant. So PV is directly proportional to T, we got it ultimately. As a result, PV is directly, from here we conclude that PV is directly proportional to T. That is only the Boyle's law. That is only the Boyle's law. That pressure is inversely proportional to volume when temperature remains constant. Alright. So here it is nothing but PV is equal to constant, we got it. We can also say that PV is equal to constant. Clear? So for a given, when the temperature is also constant, so when the temperature is also constant, here T is constant, K is constant, 2 by 3 is constant. You can also write PV is directly proportional to T, or we can write PV is equal to constant straight away. Well, because in Boyle's law, T is also constant. Alright, K is constant, proportionally constant, 2 by 3 is a constant, so PV is equal to constant, we got it. That also we can say that. Clear? In this way, what we can say, this proves the Boyle's law. Clear? Now, next is coming to the Charles law. Next we will come to the Charles law. Charles law, we can say that. Now Charles law, what it says? Volume is directly proportional to its absolute temperature when pressure of a given mass of a dry gas remains constant. V is directly proportional to T. Volume is directly proportional to absolute temperature when pressure of a given mass of a dry gas remains constant. Okay. Now just now we have seen it. PV is equal to 2 by 3 Kt. See here. We got PV is equal to 2 by 3 Kt, where K is proportionally constant, so to say. So I can write V by T. Alright. V by T, what is that? It can be nothing but 2 by 3, that is K, what you can say, K by P, cross multiply, PV is equal to, you got it, 2 by 3 Kt, you will be getting it. So V by T is equal to 2 by 3 Kp, we got it, fine. Now 2 by 3 number constant. K is proportionality constant. For a what you can say for Charles' law, what I said, pressure remains constant. So hence V by T is equal to constant. Again, just like Boyle's law, in Charles' law we got it. V by T is equal to constant. So it verifies also the Charles' law. Got it? Clear? So next, after that, we will see the Dalton's law of partial pressure. The Dalton's law of partial pressure. Now, what does Dalton's law says us? Dalton's law says that in a particular container, when number of gases are present and these gases do not combine with one another, then the total pressure exerted by the container is the sum of the individual partial pressure taken together. Got it? Let me say again. When in a particular container, a number of gases are present and the gases do not intermix with one another, they do not combine with one another. These gases, uncombined gases, so to say, we have studied already. Then the total pressure exerted by the container is the sum of the individual partial pressure taken together. We can say that. Now we know this is your Dalton's law we are going to do. So we already know Dalton's law partial pressure. Okay, so already from the kinetic gas equation we know PV is equal to 1 by 3 mn c square. P is equal to 1 by 3 mn c square by V. Now for different gases, in a particular container, number of gases are present, so volume remains constant. Because what I am saying, in a particular container, number of gases are there, so volume is constant. What is going to differ? Pressure. P1 is equal to 1 by 3 m1, mass will differ, number of molecules also will differ, and what you can say is that C1 square by V. We can say that. That is nothing but P1 is equal to 1 by 3 m1 n1 C1 square by V for a particular gas. We can say bit 1. For another gas, let us say P2 is equal to what it will be? 1 by 3 m2 n2 C2 square by V. We can say. For the third, what you can say, gas, we can say that what it will be getting it? P3 is equal to 1 by 3 m3 n3 C3 square by V. We can say that. So when I add it, that is P total is equal to what? I'll add it, this equation 1 and 2. Equation 1 and 2. The equation 1 and 2, when I'll add it, what will I get? I'll be getting P1 plus P2. Equation 1 and 2. What is equation 1? This 1 by 3 m1 say n1 c1 square by V plus 1 by 3 m2 n2 c2 square by V. So what is this? This is equal to P1. And what is this? This is equal to P2. So P total is equal to 1 plus 2, bit 1 plus bit 2. That is nothing but P1 plus P2. That is only Dalton's law of partial pressure, which says that the total pressure exerted by the gases in the container is equal to the sum of the individual partial pressure taken together. Finished? So in this way, this is your Dalton's law of partial pressure. We have explained it on the basis of the kinetic molecular theory of gases, so to say. We have explained it on the basis of kinetic molecular theory of gases. Now, we have finished up with this. Now we'll come to the behavior of the ideal gas and the real gas. Behavior of ideal and the real gas. Now, next is, ideal gas. What is that? Ideal gas is a gas which obeys gas laws under all conditions of temperature and pressure. Under every conditions of temperature and pressure. And I said you earlier also that this particular ideal gas, whatever we say, it is completely theoretical. It is not possible. There is no such gases which will obey gas laws under all conditions of temperature and pressure. Then what are those gases? All those gases are the real gases. What are real gases? Real gases are those gases which obeys gas laws under certain conditions of temperature and pressure, not under all conditions of temperature and pressure. So basically all the gases which we are studying, hydrogen, oxygen, nitrogen, everything, got it? So they are all real gases. They are not the ideal gas, they are the real gases. We can say that. Got it? So under what you can say, low pressure and high temperature, only a particular gas behaves as an ideal gas. Remember the conditions. Under low pressure and high temperature, a particular gas can behave as a, what you can say, an ideal gases. Got it? But there are certain gases which shows a deviation from this particular thing. There are certain gases which shows a deviation. there are certain gases which shows a deviation. Now, in certain gases, the deviation is quite large. In certain gases, the deviation is quite small. We can say that. Like suppose the gases which are highly soluble in water. Listen carefully, children. The gases which are highly soluble in water, alright, or easily liquefiable, the one which can easily liquefied. Alright, again I repeat, the gases which are highly soluble in water, the gases which are easily liquefiable, like I can give it to you, carbon dioxide, sulfur dioxide, ammonia, these gases. Alright, you have read in the lower classes. They have got low, what you can say, that is liquefiable point. They liquefy very easily. Under low pressure only they get liquefied. Under low pressure and low temperature only they get liquefied. Alright, so the gases which are easily liquefiable, like this particular gas which I gave you, like carbon dioxide, sulfur dioxide, ammonia, they show a large deviations from the ideal behavior. Alright, they show a large deviations. Alright, so larger deviation. Then the gases like what you can say, the non-polar gases like hydrogen, oxygen, nitrogen, methane, these are the non-polar gases, you know that. They show, they also show the deviations. These are gases also show the deviations because all these are real gases. I said you earlier only. But the gases which are easily liquefiable, which are easily soluble in water, which are more soluble in water, they show a larger deviation than these non-polar gases like hydrogen, nitrogen, oxygen, methane, etc. We can say that. Got it? So hence I said you that ideal gas equation is PV is equal to nRT. So this particular equation is will be true. This particular equation will be true when the pressure is low and the temperature is high. So basically the real gases behaves as an ideal gas under these conditions. When the condition is reversed, then there is a deviation. Then there is a deviation. The deviation which I was talking to you, then there is a deviations. Alright, when the condition is reversed. Now we will come to the study of the deviation. I think you understood what is the ideal gas and what is a real gas and what should be the condition. Again I repeat, low pressure and high temperature, under these conditions only a particular gas behaves as an ideal gas. It shows an ideal behavior. Otherwise, under high temperature, under high pressure and low temperature, they behave all as real gases. Got it? Clear? Now we are going to study about it, that how they show these particular deviations. I said you that certain gases show larger deviation, some gases show deviation, but it is less. Okay, fine. To study this deviation from the ideal behavior, to study this deviation from the ideal behavior, we will take a particular gas law and we'll explain it. So you know that we have taken we know the Boyle's law, PV against P. So this is a Boyle's law graph. Now in case of Boyle's law graph, you know this is a straight line graph, I will be getting it. Alright, let me draw it a little bit below. A straight line graph, I will be getting it. This is a Boyle's law graph if you remember it. PV remains constant. Alright, PV remains constant. PV is equal to K. Just now I told you also, according to the kinetic molecular theory of gases. So in this way, what I find is that one particular law I have to take it and I have to explain the deviation from the real gases from the ideal behavior. Listen carefully, repeatedly I am saying you. Alright, so what I find is that here this line which I have done it is for which gas? This is for ideal gas. I'll prove it also how it is ideal gas. So in this way it is for the ideal gas, because what I said, ideal gases are the gases which obeys gas laws under all conditions of temperature and pressure. So which law I am telling you? This graph depicts which law? Boyle's law. PV against P graph, we will be getting a straight line graph. Under what condition? When PV is equal to constant. We have done it already in the Boyle's law. You go back to the Boyle's law and you see it. We have done this particular graph. We have seen this particular graph. Even if you don't understand, I have explained to you also just now in the kinetic molecular theory that PV remains constant. We can say that. So in this way PV remains constant. So here this graph you can see is for the ideal gases. Fine. Now any gases above this, below this shows deviations from the ideal gases. Any gases having the graph above this, having the graph below this, shows deviation from ideal behavior. It shows deviation from ideal behavior, so to say. Now, if you draw it, you will find like the non-polar gases like nitrogen, hydrogen, they show deviation from ideal behavior in this particular manner. Alright, the graph is in this manner. Now, certain gases, the one which is easily liquefiable, the gases like carbon dioxide, I said you, gases like ammonia I said you, sulfur dioxide I said you, they show this sort of graph, this sort of deviation. Now you need to understand this. Alright, you have to understand this particular part, that how they show this sort of deviations. Alright, clear? Now, before going to this particular graph, one more thing I want to tell you. Here we will be studying the compressibility factor. Now what I said you, certain gases are easily liquefiable. Which gases? I have explained you, carbon dioxide, ammonia, sulfur dioxide, these are the gases. Etc. also, many more gases are there, like HCl and all, we are also there. So they are easily liquefiable compared to non-polar nitrogen, hydrogen, what you can say, oxygen, methane and all these gases which are non-polar in nature. Fine. Now, for liquefying a particular gas, what should be the condition? The condition should be, temperature should be low and the pressure should be high. Temperature should be low and the pressure should be high. It's different from the ideal behavior you see. What I said, a particular gas behaves as an ideal gas under low pressure and high temperature. Mind it, under low pressure, high temperature, it behaves as an ideal gas. But what I am saying you here, for liquefying a particular gas, pressure should be high. You have read it in the lower classes also. Liquefaction, the process. How do we liquefy a particular gas? When the pressure is higher and temperature is low. When the temperature is being lowered and the pressure is being higher, then only the gases gets easily liquefied. This is a condition for liquefying a particular gas. Pressure should be high, temperature should be low. That means it is a deviation from ideal behavior. The condition is different from the ideal behavior. Now, based upon this particular conditions, we are going to calculate a factor which is called as compressibility factor, denoted by the letter Z. This is called compressibility factor. Z stands for compressibility factor. How do we calculate Z? Z is equal to PV by nRT. Z is equal to PV by nRT. We can say that. Okay, compressibility factor Z. Now, in case of ideal gas, PV is equal to nRT. Compressibility factor Z is equal to PV by nRT. This is a formula for the compressibility factor, PV by nRT. Alright, compressibility factor. Now for ideal gas, what is the formula? The gases which are ideal in nature, what is the formula? What is the ideal gas equation? PV is equal to nRT. Now you put the value here. In place of Z you put the value. What is that you put it? In place of nRT you put PV. Or in place of PV you put nRT, whatever it is going to get cancelled. For ideal gas, the value is going to get cancelled. Alright, again I repeat, this is your compressibility factor Z. This is a formula, compressibility factor Z. We have calculated it. It is being calculated practically. And this is a formula for the ideal gas equation. PV is equal to nRT, you know that. Now you put this value here. You put it here. So in place of nRT you put PV. So PV gets cancelled. Z becomes 1. This is for what gas? For ideal gas. The value of Z is 1 for ideal gas. So here see, this is Z is equal to 1. This here Z is equal to 1. I said that I will be proving it. See, I proved that Z is equal to 1. This line, it's an ideal gas. Now that means this value is Z greater than 1 and here this area is Z less than 1. Alright, this area is above this, greater and below this, it is less. So here it is, the value of Z is greater than 1 and below this value of Z is less than 1. See, this is the line I am taking. This is the line I am taking. So above this is Z greater than 1 and below this Z is less than 1, definitely. So in this way, here the compressibility factor is greater than 1 and here the compressibility factor is less than 1. When I say the compressibility factor is greater than 1, compressibility factor is greater than 1. That means compressibility factor is more. It is more. So when the compressibility factor will be more, alright, then what is the nature of the gas? Understand it. When the compressibility factor is more, what is the compressibility factor required? Temperature should be low, pressure should be high. Now this factor should be more. When this factor will be more? When the gases are not easily liquefiable. When the gases are not easily liquefiable, because when the gases will be easily liquefiable, then easily you can compress it. Then the compressibility factor will be less. Means for compressing, what are the factors required? What is the factor required? Repeatedly I am saying you, temperature should be low, pressure should be high. So this factor will be less for the gases which are easily liquefiable. But what I am talking to here is Z greater than 1. Z greater than 1 means compressibility factor is more. It will be more for which gases? Means temperature should be much lower and the pressure should be much high. That means Z greater than 1 means the factor which is required for compressing a gas, that is more. Means what is the factor required? Again I am saying temperature should be low and pressure should be high. That should be higher. So when it will be? When the gases are not easily liquefiable, then only you will be requiring very low temperature and very high pressure so as to bring the gases closer to each other. That means the gases which repel one another, listen carefully, the gases which repel one another, they do not have any intermolecular forces of attractions among themselves. The gases which do not have any intermolecular force or which have got very less intermolecular force of attraction among themselves, so the gases, they will come very close to each other easily, then they are easily liquefiable. But when they are not coming closer, rather when you are bringing them closer, they are going to repel one another. Which gases? Non-polar gases, hydrogen, nitrogen, oxygen, methane, they are the non-polar. They will not come closer. You have read it already in the previous chemical bonding chapter. The different types of forces, Debye forces, London forces, dispersive forces, got it? Kissam forces we have studied. So what you find is that here it is between non-polar and non-polar molecules. Suppose we have taken hydrogen gas. So all are non-polar in nature. So hydrogen and another hydrogen molecule, they are non-polar. Now you cannot bring closer to each other very easily. Why? Because they are not having an intermolecular force of attraction among themselves. So here the compressibility factor is high. That means you have to lower the temperature like anything. You have to increase the pressure also like anything. So the pressure should be very, very high and temperature should be very, very low. So here the value of Z is greater than 1. So remember it. When the value of Z will be greater than 1, you may write it down. The value of Z will be greater than 1 when the gases are not easily liquefiable. That means the gases are non-polar in nature. These gases, nitrogen, hydrogen, oxygen, methane, all these gases which are non-polar in nature, so to say. Alright, and they have got very least intermolecular forces of attraction between them. Then that means they are repelling one another. Those gases. The compressibility factor is greater than 1. You can see compressibility factor greater than 1. See, the graph is going upward. See that graph is upward for this particular is nitrogen, hydrogen. If I do for oxygen also, the graph is upward. But there are also gases, got it, which are easily liquefiable, like carbon dioxide, ammonia, sulfur dioxide. These are easily liquefiable gases. The compressibility factor is less than 1. Z is less than 1. It is less than 1. That means those gases which are easily liquefiable, those gases which have got high intermolecular force of attraction among themselves, there the compressibility factor is less than 1. Because you can easily compress, no? They are easily brought closer to each other. Because what I am saying, they have got strong intermolecular force of attractions. If you have taken number of sulfur dioxide gases, sulfur and dioxide and sulfur dioxide, they are pulling one another. So hence they are easily liquefiable. So there the Z is less than 1. Got it? Now the question is why the graph is increasing? Why it is decreasing? Okay, it is decreasing. Z value is decreasing, then why it is increasing? Why it is increasing means that is only the deviation. It shows from the ideal behavior. That is only the deviations, because you cannot compress a gas, you cannot liquefy a gas to any extent. To a certain extent you can liquefy the gas. Suppose you are applying a pressure, the gas gets liquefied, sulfur dioxide gets liquefied, carbon dioxide gets liquefied. Then after that if you increase the pressure, what will happen? Will it liquefy further? Already it has got liquefied. So in that case it is not going to liquefy further. So in that case the graph is going to rise up. So in case of sulfur dioxide and carbon dioxide and ammonia, the Z value is less than 1. So hence when you are increasing the pressure and lowering the temperature, the gas is going to get liquefied. But once it gets liquefied, then what happens? The graph rises up because it cannot be liquefied further. Alright. So if you increase the pressure in that case, though it is not liquefying, then the graph is going up. We can say that. So hence it shows deviation. So understood now? When the value of Z is greater than 1, when it is less than 1, when it is equal to 1. Okay. This is the deviation and real gas source from the ideal behavior. Got it? Thank you.